Magnets. Oh, fun science toys. We used to, in Science, I think 9 or Science 10 in the old curriculum, do a whole thing playing with magnets, and kids loved it. Who doesn't like playing with magnets? They're cool. Anyways, turns out magnets are dipolar. They have 2 poles. Does anybody recall the 2 poles of a magnet? We call the first one north. What do we call the second one? Take a guess. Okay. So here's a north pole. Here's a south pole in a bar magnet. And much like in electricity, like poles attract. Sorry, like poles repel. Unlike poles attract. So that already explains this phenomenon. Let me pause the video. So Shaq, where is it different from positive and negative charges? Here's the first one. Unlike electric charges where you could have a positive charge all by itself, a proton, or a negative charge all by itself, an electron, we believe it is impossible to completely isolate a north pole or a south pole. You can't have them on their own. They always come in pairs. If I were to cut this magnet or break this magnet like that, instantly that would become a north pole and that would become a south pole, and I would have 2 smaller magnets that were still bar magnets. We don't believe that you can separate one pole from another. Much like with electricity, I've just showed you magnets moving things around without touching them. Grayson, much like with electricity, we have action at a distance. How? We have to again talk about fields, invisible lines of force that we can't see that reach out invisibly like the tentacles of an octopus all the way out to infinity. Except magnets give out magnetic field lines. And you may recall that with electric field lines, we had to define a direction. What was the direction of an electric field line? We defined it. We said, oh, the direction of electric field will always be which way a positive would want to move if it could. Okay? What are the directions of magnetic field lines? What are the directions of magnetic field lines? They're defined. What's the direction? Always from north to south. So you'll make a little note, put a star next. You need to memorize that, although you will. Always from north to south. Or the other way it's expressed is the direction. And you can express it in terms of a compass. If you want to express it in terms of a compass, a compass points south. Wait a minute, Mr. Dueck. I have a compass. It points north. No, it doesn't. Mr. Dueck, I hate to argue with you, Mr. Dueck, but I've gone camping. I've pulled out the compass, and that needle is pointing north. No, it's not. Mr. Dueck, again, I don't want to belabor a point here, but I always understood that compasses point north. Compasses point geographical north. They do point towards the North Pole-ish. But what does that mean? It means that if you imagine the Earth as a magnet, here is what the Earth looks like inside. At our geographic North Pole, that is the South Pole of the Earth's magnet. And at our geographic South Pole, that's where the North Pole of the Earth's magnet is. The reason your compass points this way towards the geographic North Pole is because compasses point in the direction of a magnetic field. Oh, and magnetic fields always point from what to what? North to south. I don't know if you knew that, but the Earth inside is exactly the opposite of what you thought magnetically. Geographic north, yes. Magnetic south. Symbol for magnetic field. Well, we can't use M for magnet because what's M been taken by? Mass and meters and mega and milli. M's taken for any variation, so that's not going to work. F for field. No, F's taken by which concept? Force. So, what symbol? Well, not all physics was done by English-speaking people. The symbol for magnetic field is a capital B. In fact, you'll hear me talk about a B field as an abbreviation for a magnetic field. And the units, magnetic field is measured in Teslas, symbol capital T. There are other ways to measure magnetic field. Another accepted unit is a Gauss, named after a mathematician whose last name was Gauss. But the one we use in our standard, there's also a math contest named after him. The standard one we use in physics, though, is a Tesla, named after one of my favorite, very unusual, very weird scientists. The Earth's magnetic field, that which can cause a compass to move, is around, it varies a bit, but I'm going to say 10 to the negative 5 Teslas, 0.00001, actually sometimes even smaller. A very large field, a field that would be big enough to probably start to affect the metal in your body and probably have biological consequences. For example, your hemoglobin has iron and maybe your blood wouldn't flow the way it normally should. 50 Teslas would be, certainly to long-term exposure, probably fatal. So 10 to the negative 5 is enough to move a compass. 50 is enough to change your body. I always, whenever I give you a new concept, Nate, like to tell you what's really big and really small. So a 50 Tesla field. I will be showing you later on a video, and I think it has a 3 or 4 Tesla magnetic field. It's strong. Put your pencils down. It turns out there are 2 main types of magnets. Permanent ones that are made out of ferromagnetic materials. These are the ones that you use on your fridge. These are the ones that I have here for you to play with. They're cool. Far more useful, though, are electromagnets. This is a magnetic field caused by a current, and the reason this is so useful, this gives us a magnet that we can turn on and off. The video you saw of the MRI machine, that's a very powerful electromagnet. Hugely useful. If you asked me to list the top 10 most useful electric inventions in the past 150 years, I think the idea of a solenoid, which is a fancy electromagnet, would be one of them. They're used all over the place, and I'll try and show you where they're used. What do magnetic field lines look like around a single magnet? Remember we said magnetic field lines point from what to what? So here's a picture. You can see the lines are pointing from north to south. They're bending as they want to get towards the South Pole, pointing from north to south. So as you can see, from north to south. This is also the direction a compass would point if you put it in that location on the diagram. So if you plunked a compass right here, it would point that way. If you plunked a compass right here, it would point that way. You can use a compass to detect a magnetic field. And actually, it turns out, I think a lot of your smartphones, the newer ones, also have a built-in magnetometer that'll detect magnetic field. I noticed just yesterday I downloaded an app for my Android called Physics Toolkit, and it claimed to have a magnetometer, so I turned it on, I brought it close to my fridge magnets, and it did peak, it did spike. So I got to see how accurate it is, because I'm a nerd, but absolutely, some of your phones might have that too. Another thing, unlike electric field lines, magnetic field lines have no beginning and no ending. Wait a minute, Mr. Dueck, it looks like they end to me. Actually, no. Raffi, each of these lines continues through the object and comes out the other side, which also means the magnetic field inside the object is the opposite direction of the magnetic field outside the object. They all continue. They have no beginning and no ending. At least none that we've ever been able to create. If we could separate north and south poles, then they would. But as far as I know, and I haven't read in the last few years, but certainly when I last checked, we did not believe it was possible to have a separate north and south pole. They always exist in pairs. The Earth is also a magnet, which is how a compass works. At the North Pole, what does the magnet inside the Earth look like? Which magnetic pole is up north? Make that a better N. It's exactly the opposite of what you thought. So that's why magnetic field lines point from what to what? So the Earth's magnetic field would look like that. And that's why a compass, which will point in the same direction as the magnetic field, a compass will point north, geographically, which is magnetic south. Let's draw in the magnetic field lines below. Here are two bar magnets. Are the two closest poles to each other like or unlike? Like, so are they repelling or attracting? So it would look something like this. And some of these lines would continue on here. They would come back on the page here. They would come back on the page here. But specifically what you would notice is this particular pattern. You would see two magnets and magnetic field lines facing each other. You would say, oh, they're repelling each other. I think I have a sim for that. Let me double check. Symbols. One of the difficulties, maybe the only tricky part of this, Mickey, is that it turns out magnets act on other objects in 3 dimensions, not in 2 dimensions. But we have to draw these on a 2-dimensional piece of paper. So here is the convention that we have decided to show that something is going into the page. What we do is a circle with an X. And that's designed to be the tail feathers of an arrow going away from us. We're looking at an arrow going away from us. We're looking at the tail feathers. Or sometimes, Joseph, we won't even bother doing the circle. So if you saw that, that would be a magnetic field going into the page. Yeah, we've turned the page. I know my audience. The symbol that we're going to... the symbol for to the right is still an arrow pointing to the right. The symbol for up is still an arrow pointing up. But we're going to need to do 3-dimensional directions. So how can we show into the page? Tail feathers of an arrow going away from us. How can we show out of the page? A circle with a little dot. That's the tip of an arrow coming towards us. Or you may just see the actual dots themselves. That's a magnetic field coming towards us out of the page. And until you get good, what I'm often going to say, because you're matching it to my overhead screen and my overhead projector screen is vertical, you're even going to hear me yell, okay, hold your paper up vertically for some of these just so that we can orientate this, because the tricky part of this, Zach, is wrapping our brain around 3-dimensional pictures on a 2-dimensional piece of paper. Electromagnets. I said to you that electricity can cause a magnetic field, and it does. And the first one, any wire carrying current automatically creates a magnetic field. A current carrying wire generates a magnetic field. If you put a compass near a wire, it will be deflected if the wire is carrying current. Now, if it's carrying alternating current, that means the current is going this way, then 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 this way. What you have is an oscillating magnetic field that's flipping back and forth so quickly that the net effect is 0. But if you have direct current, you actually have to take that into account, especially if you're building stereos and radios. This is where you get some of that electric noise or squawk from a poorly designed direct current circuit. And this brings us to the first question. I will ask you this on the test. I like this question. I like this question. I like this question. I will ask you, what direction is the magnetic field created by a current carrying wire? And the way you figure it out is with something called a right-hand rule. A right-hand rule. To do this right, Mark, you want to get your hand far away from your body and make your gestures big. If you want to get this wrong, keep your hand out tucked in. So what's the right-hand rule? I'm going to stand up. We're going to use this as our piece of paper, the front of the room. What you do is you point your right thumb in the direction of the current. So here is a wire. What direction is that current? What does an X into the page mean? The current is into the page. Point your right thumb this way. Not this way, Naomi. Point your thumb at me. Yes. You have to bend your elbow if you have to. Okay? Point it at me. Right thumb. Your fingers curl in the direction of the magnetic field. So try it with your piece of paper right now. Point your thumbs at your piece of paper. Point your thumbs into your piece of paper. Your fingers curl in the direction of the magnetic field. The magnetic field is going this way. There are 3 right-hand rules. This is the first one. This is the easiest one. This is where the other 2 end up coming from. Okay. Example 3. Here, the wire is going horizontally, and I've given you the pictures of the magnetic field. What do those dots in the top row mean? What direction is the magnetic field coming from? Towards us. What do those X's mean? Okay. All of you hold your paper up vertically, please, with your left hand. Hold the paper up vertically with your left hand so it matches my screen. What's the magnetic field right here? Curl your fingers so that they're coming towards you above your thumb and going away from you below your hand. What direction is my right thumb pointing? That's the direction of the current. Has to be. I got more practice, trust me. Okay? The right-hand rule says you point your thumb in the direction of the current, your fingers curl in the direction of the magnetic field. If I have a wire and the current is going this way, the magnetic field curls that way. If I have a wire and the current is going that way, the magnetic field curls this way. And I apologize for those of you who are watching this on YouTube because you're going, which way? Which way? You need to see me in person because I cannot explain this on YouTube. I've tried. Okay? You have to be here in person. Sorry, geography field trip people. That also works for a proton. A proton, because current is which way positives would flow if they could, a proton moving that way creates a magnetic field. What if we're talking about electrons moving, like in Alberta or Saskatchewan? And this is what you were taught. You can either use, they teach a left-hand rule, which is confusing. Or, you know what? Electrons moving down mathematically are the same as protons moving which way? I just I just point my thumb in the directions that positives would be moving, and I can continue to use my right-hand rule. I prefer that method. So, in this picture here, current is going up, which does mean, Nick, in Alberta and Saskatchewan, electrons would be going down. Electrons down, that's the same as current up, and there's the lines of magnetic force. There's the magnetic field lines. There's the lines of a compass needle. We need to practice this. I have another handout. So here's the handout that I gave you. It's called Right-Hand Rule Questions. We're going to jump around a little bit here. I don't want Dropbox to be open. Shrink back down. There we go. We're going to get to those. Can't do that one yet. Can't do that one yet. Number 6, please. Here are the kinds of test questions you can expect. Number 6 says, which of the following diagrams best illustrates the magnetic field around a wire carrying conventional current? That means we're not talking about electron flow, we're talking about protons in the direction shown. Can you see the center dot is the wire in all 4 pictures? All right. Which way is the current coming in all 4 pictures? Number 6, which way is the current coming in all 4 pictures? So point your right thumbs out of the page. What direction are the magnetic field lines? A, B, C, or D? So for me, I would do this. And what's the correct answer? A. Number 10. Number 10. Number 10 says, first of all, both of these are in the plane of the page. What they're saying is, assume there's a flat circuit. We're looking down at it like it's sitting on a table. What direction is the magnetic field at point P? First of all, point P, is it closer to the bottom wire or the top wire? So the bottom wire is going to be the dominant magnetic field. Which way is the current? This way, this way, this way. Oh, that way. In the bottom wire, current is to the left. Point your right thumbs to the left. And at point P, if you were holding the wire in your hand right along your thumb, what direction are your fingers curling? So for me, if I point my right thumb, I am pointing this way. A, right? I'm pointing into the page. I'm not pointing out of the page. I'm not pointing down the page. I'm not pointing up the page, into the page. Number 10, the correct answer is A. Like crazy, all the time. No, not here. Oh, sorry, are you just talking from this wire or from both? If you're from this wire, here it's going to go into the page. On this side, below the wire, it's coming out of the page. Yeah, and this is, Nick, it's a 3-dimensional situation that we have to represent on 2-dimensional paper until we have our holodeck someday. But right now, this is what we're stuck with. Let's try another one. Number 14. Try number 14 on your own, please. Try number 14 on your own, please. Now, this one, I guess the current is going kind of slanty to the right and down. So point your thumb kind of slanty to the right and down. For me, now if you're having trouble with this, you can always hold your paper vertical so you can match my screen. So I would go like this. A, yes? Not B. B is the opposite direction. And C and D are just distractors. F, A. Make sure you use your right, not your left. It happens every time. Okay? By the way, who are my lefties here? This is one of the few times you have a huge advantage because you can do the direction with your non-writing hand and keep your pencil in your writing hand. It's one of the only times we have an advantage. Woohoo! Number 17. Number 17. Try number 17 on your own. Try number 17 on your own. So the current is moving towards the right. If you're not sure, hold your paper vertically to match my screen. And it looks like above the wire, my fingers are curling out of the page towards me, which I symbolize with dots. And below the wire, my My fingers are curling into the page away from me, which I symbolize with X's. What's the correct answer? A, B, C, or D? D. Which hand do you write with? Okay, so it's the hand you write with. Number 18, which kind of is half on one page and half on the other. So I'm not sure if you have to turn the page to get to the question or not. This is not a right-hand rule question necessarily. This is just saying what direction is the magnetic field at point P because of the bar magnet. Magnetic field lines always point from what to what? So if you start drawing here in the north and you make a nice little loopy picture until you hit to the south, what direction is the magnetic field right at point P? Up the page? No. Down the page? No. Towards the left? Towards the right. Now, inside the magnet, it keeps going that way. What would the direction of the magnetic field be right there? To the left? Try number 19, please. How can you figure out which one is north, which one is south, or if they're both the same? Which way do magnetic field lines always point? From what to what? From north to south. So, no, no, yes, 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 no, yes, no. C, right? Back to our notes. Pardon me? Eventually, but have patience, young grasshopper. You can't do the rest of them yet because there's 2 more right-hand rules to go. This handout is because I needed to find a whole bunch of examples, so I went through old provincial exams that you haven't seen before. That's the right-hand rule for a current carrying wire, or right-hand rule number 1. The next question we ask, the next electric device we're going to give you is something called a solenoid. Hugely, hugely useful electric device. What's a solenoid? Well, a long time ago someone said, well, hey, if one wire gives me a magnetic field, what if I wrap a bunch of them around something in the same direction? And that's what a solenoid is. A solenoid, if we coil the same piece of wire around and around in many loops, all in the same direction, we call this a solenoid. And the next question we're going to ask ourselves is, okay, it turns out this also generates an electric field significantly larger. What direction is the magnetic, did I say electric field? Magnetic field, significantly larger. What direction is the magnetic field created by a solenoid? We're going to need another right-hand rule. Here's a typical solenoid. Turns out also we can dramatically increase the strength of the magnetic field by adding an iron core at the center, because that also becomes magnetized. We call this an electromagnet, and it has, cross out the word thousands, millions of uses. Millions of uses. This here, one of the most useful electric devices ever invented. So, how do you figure out the direction of a solenoid? Here is the right-hand solenoid rule. This is right-hand rule number 2. You imagine holding the solenoid in your hand. Here's my coil of wires. You imagine holding it in your right hand. What hand, Mickey? Your right hand. You curl your fingers in the direction that the current is going through the wire, and they'll tell you. Your thumb points north. You curl your fingers in the direction that the current is going through the wires. Your thumb points north. Let's try it. Example 4. Mr. Dueck, you didn't give us anything. I always give a blank solenoid just to show you how you can draw a solenoid. So here's how we're going to draw a solenoid. Here's our iron core that we're going to wrap the wire around. Let's put a battery down here, like that. And let's have the wire go like this, and we'll have it go over the top and then duck behind. And then the trick to making these look three-dimensional is to do big, long S's. Look up and just watch. Here's what I mean. There's a big, long S. There's a big, long S. It's a backwards S in this case, but this is the trick to making these look three-dimensional. There's a solenoid. Okay, draw that. You'll get a picture that looks something like this. Big, long, elongated, skinny S's, or backwards S's in this case. Right? I mean, that looks kind of 3D-ish, yes? I mean, as good as you're ever going to see me draw anything. So, how can I figure out the direction of this solenoid's magnetic field? First thing I have to do is fill in the current. So once you've got this written, look up just so I know everybody's copied it out. Naomi, you got it? Because you're always drawing. Yeah? Okay. I've seen your notes. Everybody got it? So, see the battery at the bottom? Which way is the current leaving the battery, to the left or to the right? Okay? And again, Nick, I'm going to argue this is far superior to the to the right. So all of you draw an arrow pointing that way. So I guess that means the current is going up here, up, 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 up. It ducks behind, but I think if I follow it, it's going this way, this way, this way, this way. Double check me, am I correct? Yeah? So let's use this as our piece of paper. All of you imagine holding the solenoid in your hand. You can hold it one of two ways. You can hold it this way, or you can hold it this way. Curl your fingers in the direction of the current. I think the only way that works is if I hold it this way. Right? If I hold it this way, my fingers are coming over the top towards me. Again, I apologize to those of you at YouTube. But if I hold it this way, my fingers are curling away from me, just like the current. Which way is my thumb pointing? To the left? That's north. That's the right-hand solenoid rule. If you go back a half page to this one here, the current is flowing this way, and if I look really, really close, I think the current ducks behind and comes over this way. I think it's pointing to the left when it comes over the top. So if all of us will use this one here, how would you hold that? You can either hold it this way or this way. Oh, no, my fingers are curling the wrong way. Yep, my fingers are curling the right way. Which way is the North Pole on this solenoid? Top or bottom? Bottom. I think I got... I have some more examples in a second, but where do we use these? Well, first of all, what if instead of hooking this up to a direct current, what if you hooked it up to an alternating current? You would then have a magnetic field that pointed this way, then that way, then this way, then that way, then this way, then that way. So if you had another magnet right here, it would get repelled, then attracted, repelled, then attracted, repelled, then attracted. It's how all your phones vibrate. They all have a solenoid in there. Or if you go look at the old the fire alarm bells, all that is, if you take away that orange piece of metal, there's a solenoid inside there. In fact, my friend lives in a very, very old apartment building, really old. And so I took a picture of his old style solenoid alarm bell. The only difference with the ones in the school is this contraption is actually behind the bell inside now. But here's an alternating current. There's a magnet right on the end of this pivot right there that gets repelled and attracted, repelled, so it gets pulled left, right, left, right, left, right, and that makes us go ding, 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 ding. There. Old doorbells, the old phones that actually used to ring. Or if you don't hook it up to an alternating current, if you hook it up to a direct current, where can they use this? Your power door locks are a solenoid. When you push the door lock down, the magnetic field points this way, and the magnet pulls whatever piece of metal down, your doors are locked. When you push the door lock in the opposite direction, they just flip the current, now it repels the magnet, the door lock is now pushed up, it's open. These are used all over the place. So I wrote down here, we use them in transformers, not the toys, the actual electric devices. That's going to be coming later. Motors, generators, televisions, speakers, doorbells, fire alarm bells, cell phones, power door locks, etc., etc., etc. They're used all over the place. It gives us, Rafi, a magnetic field that we can control the size of, the direction of, and turn on and off. Lets us move other stuff if we attach a magnet to the other thing. That's how we move things electronically. There's other ways, but that's one of the main ones. Let's practice this right-hand motor rule. Can you get out the second handout that I gave you, the right-hand rule questions, please? Can you look at number 9? Number 9. What number? 9. Or are you saying no? 9. Okay, we're back. Solenoid. First thing I always do, Shaq, and trust me on this, please, draw the current in. You'll do it wrong. You'll make a mistake if you don't. So I'm going to go, okay, current goes this way. Ducks underneath, comes over the top. I think the current is going like this. If you don't do that, you're setting yourself up for yuckiness. So, am I holding it right this way? No. Am I holding it right this way? Which way is the North Pole outside the magnet? On the, so let's draw a little north right here, a little south right here. We can certainly answer the right-hand column. The North Pole is at which letter? So yes, no, yes, no. Now, the magnetic field lines go like this. From north to south. And remember, I said magnetic field lines have no ending. So inside the solenoid, the magnetic field line goes that way. What direction is the magnetic field inside the solenoid? Pointing to the left, or from what letter to what letter? No, no, yes, yes. Outside, say at the top, yeah, it's pointing from X to Y, but inside it, the opposite way. I think I have one more solenoid. Maybe not. Let me double check. Nope, only one. Okay. Whew. 15 minutes. The yuckiest one is next, and I'm going to pause because I really don't want all these kids away.